Oxidation reduction reactions involve a change of charge. And what I mean by this is that one metal may begin with a charge of 0 and end up with a +2 charge. And another metal may start with a +2 charge and end up with a 0 charge. That's what I mean by changing the charge from the reactant side to the product side. Now this stuff can get a little bit confusing, so let's go through this step by step. One of my favorite ways to tell what an oxidation reaction is doing is a little synonym, and that is Leo the lion goes grrr. Okay, and what that stands for is loss of electrons is oxidation, that's your Leo, and gain of electrons is reduction. So let me show you what that means. Let's say that we start with cobalt right here, and it's a solid. Well, notice it doesn't tell you that there's a charge, so we can assume that that charge is 0. I'll get to this in a minute, like sort of how we tell those things. But cobalt goes to +2 on the product side, which means that if you're going to balance the +2, there are 2 electrons that were lost in that reaction. So over here, he's holding on to those 2 electrons, and over here, he lets them go. So that cobalt lost 2 electrons. And so the loss of electrons is oxidation. That's a Leo. Okay? On the other hand, if you have cobalt that starts off with a +2 charge and it gains 2 electrons, so these two things are added together in order to get a final product that would have a 0 charge, that's a gain of electrons. So you're adding it on the reactant side, it gains it, it combines with this to give you what your product is. That's a gain of electrons and is talked about as a reduction. So that's what that means, is it's a reduction. It's kind of backwards because you're gaining electrons, therefore you're reducing the charge, and sometimes that's a little bit confusing, and that's why this is a harder topic. But in reality, chemicals don't react in isolation, right? They react with each other. So when one thing is happening, another thing is happening simultaneously. So in other words, usually one metal will start off with the electrons and pass it to another metal. And in that process, one goes through oxidation and one goes through reduction. So let's try an example. Let you see right here. Copper right here is by itself. And I just told you that anything that's by itself, if it doesn't tell you what the charge is, it's 0. I'll tell you that again on the next page, but that's okay. And over here, this silver is 0. But I think we all know that AgNO3 by now should have a positive +1 charge on that Ag because NO3 is minus, right? And over here, I hope you all can tell that this copper, because there's got 2 NO3s, is a +2 copper. Because remember, NO3 is minus? Okay. Then I broke this down into the 2 reactions that you see here and here, just like we saw above there. So I kind of just separated things out into what's called a half reaction, but you don't need to worry about that yet. Forget about NO3, he's not changing, he still has a negative charge to him, so we don't have to worry about him. But in this reaction from above, copper, we said, started out as 0, remember? And it goes to a +2. So to balance that out, I would put in 2 electrons on the product side, sorry. And so therefore, this is called an oxidation reaction because it's losing 2 electrons. On the other hand, in this second reaction, Ag starts as a +1 and ends up as a 0. So it's losing, or it's gaining 1 electron from here to give you the 0 on the other side. And so a gain of electrons is reduction. So yes, if you're putting electrons in on the left side, it's a reduction. If you're losing them and putting them on the right side or the product side, it's an oxidation. Cool, so we got that down. Here's where another little bit of confusion though comes in. We like to say the same names again and again. I don't know why, but that's what we do. We can say that copper is oxidized or goes through oxidation. And therefore, it is the reducing agent. Okay, that means that it makes the other one go through reduction. I know, we use the same terms a lot, but that's just the way it is. Sorry guys, I don't make these rules. When it comes to the reduction, silver is reduced and we call it the oxidizing agent. So a lot of times what we'll say is this is reduced and over here we call it the oxidizing agent. ENT. Okay. So how did I know about these charges and where to get them from? If that was something that you were sort of lost with, let's look at what those rules are and how to determine oxidation state. Before we start, the simplest thing to start with is that an oxidation state is basically charge. That's all we're really talking about if you hear about the term oxidation state. And any pure element has an oxidation number of 0. So any metal that's by itself, but also things like H2, Cl2, N2, O2, F2. All of those would be an oxidation number of 0. In other words, 0 charge. Monoatomic ions that have an oxidation equal to their charge, we've already talked about this. If you have NaCl, Na would be +1, Cl would be -1. We've figured out how to determine that FeNO3 is Fe plus 2, right? And the same way that we know what that charge is to be able to name it, that's still what we call the charge now, but now we're just going to call it the oxidation state is that, okay? The oxidation number for fluorine is, I don't like that term, it's -1. So here we get into more of exceptions. Oxidation number is hydrogen is +1 unless it's combined with a metal and then it's -1. So we see how this is like Ca is first and then it's H2, that's when it would be -1. Oxygen is -2 except when you have 2 oxygens that are connected together. You're not going to see that very often though. And then that oxidation state would be -1. Okay. Cl, Br, and I are -1 unless they're combined with oxygen and or fluorine. So they're kind of like fluorine up here, just a little bit different. And the big thing is that the sum of the oxidation numbers must equal the charge for the ion or 0 if it's not indicated otherwise. So when you add things together, they should equal the charge that's there. So an example of this would be ClO3. If oxygen's -2, and there's 3 of them, which would give you a -6, then we're looking for the oxidation state of chlorine. Chlorine, and then added to that the -6, gives you a -1. I get this -1 because this is a -1. And so chlorine, in this case, has to be 5. And that's how we find out oxidation states. It's just a fancy version of charge. Okay? Kind of. Okay. Thank you very much.